Good afternoon, everyone. So I'll be talking about testing classical properties from quantum data. This is joint work with Matthias Caro and Joseph Sloat. So first, what is property testing? Property testing refers to super fast algorithms for approximate decision making. I have some very large data set, and I want to detect, does this satisfy some global structural property? So what do I mean by this? Let's say you're a librarian, and your intern comes to you and tells you that they've alphabetized the entire library. So one thing you might do to check their work is to take every single book one by one and check that all of these books are indeed alphabetized. But maybe a more natural thing to do is to take small subsections of the library and check that those smaller subsections are alphabetized. Now, if you're also a mathematician, you might ask, how many of these small checks do I need to make in order to be reasonably sure that the entire library has indeed been alphabetized? And this is the essence of property testing: super fast algorithms to decide some global property. Okay? So let me make this a bit more formal in the context of Boolean functions, which, by the way, we'll be working with for the rest of this talk. Let's say P is the set of all Boolean functions that I care about. Given some unknown function f, I want to decide, is my f in P, or is my f far away from all g that are in P? Promise that one of these is the case. So I don't really care what happens in this intermediary regime where f is kind of close to being in P but not quite in P. But between these two cases, I want to distinguish with high fidelity. So if we go back to the library example, I want to be able to tell, is the library alphabetized or is it far away from being alphabetized? Okay, now if I want to say something about my function f, I need a way to access f. So a very natural model is classical queries. So what do I mean by this? That means for any x of my choosing, any n-bit input, I can get back the value of f of x. And as you might expect, this is a very natural model. And indeed, this is where property testing has its origins with the BLR linearity test. So if you want to check that a function is linear, one way to do this is to actually learn what the linear function is. But this takes at least n queries. But if you wanted to just test whether it's linear or not, what you can do is take a random x, take a random y, and check, is f of x plus y equal to f of x plus f of y? And then the ingenuity in the work of these authors is showing that this very simple test does indeed, with high fidelity, check whether a function is linear. Okay, and these are examples of other properties that have been studied under this model, and we'll be talking about some of these later. Another natural model is quantum queries. So this is the model that we all know and love, where we have access to a unitary, and on any superposition of inputs that we want, we can apply our quantum oracle U of f. And as we might expect, as we go from classical queries to quantum queries, indeed, our complexity gets a bit better. So for example, for junta testing, we go from O of k to O of square root k. For monotonicity, we go from O of square root n to like n to the 1/4, and of course, everything else stays constant. Now, another very natural model is classical samples. So what do I mean by this? So instead of being able to access f at an x of my choosing, I instead get samples of the form x comma f of x, and most often, x is drawn uniformly at random. So I don't get to decide where I query my function f of x. Rather, I receive samples, and I must decide something about f from these samples. And this is a very natural access model for data analysis and machine learning, where you can't directly make fresh queries to f. So for example, if you have a very large data set, you can't really decide what your input and output space is, but you might want to check that your function is linear or not to decide whether you should run like a more expensive neural network or if a support vector machine will be fine, for example. There's a caveat here, though. In 2019, Eric Bly and Yuichi Yoshida completely characterized which properties are testable with just a constant number of samples under this model. And it turns out that the class of properties that are testable if you're given sample access and not query access is just rather limited. And if we go back to our list of testable properties, we see that, as we might expect, when we go from classical queries to classical samples, our complexity gets worse. So linearity, which was originally just a constant number of queries, now requires n number of samples. So I've been drawing thus far these models rather suggestively. So I have quantum queries, classical samples. You can ask the question, is there a notion of quantum samples? So in our work, we advocate for the following model as the natural quantum analog to classical sample access. So suppose we have access to the following quantum state, It's a superposition over all n-bit inputs as well as the output f of x. And we ask the question, what advantage does quantum data offer for testing classical properties? So I want to note here that you're no longer given access to the oracle, rather you're given access to these quantum states. And before I explain our results and get into more detail, I just want to talk a bit more about why we think the quantum data model is a natural model and why everyone should be exploring it. So not only do we think it's the quantum analog to classical property testing, so it's just a very natural thing to explore, but there are also some very real practical motivations. Let's say you're in a lab, you have limited time with your experimental setup, etc., and you don't know what you want to do yet with the data. Then what you can do is create superpositions of these quantum states and store it once, and then decide later on, decide later on what kind of analysis you'd like to do. So there's this post hoc flexibility in analysis. And a second very real practical motivation is you're able to distribute quantum functionality without revealing what the underlying source code is. So what do I mean by this? So in the US, so I don't know if this is common in other countries, but in the US, credit card companies assign credit scores to users based on how many loans they paid off, how do they pay off their debts on time, etc. But maybe there's a verification company that wants to check the fidelity of these credit card scoring algorithms. If they don't want to reveal what the underlying algorithm is, but the company wants to check the fidelity, one thing they can do is transfer copies of the quantum state. They're able to verify, does my function f satisfy some properties that you want? For example, is it monotone in the number of loans you paid off, for example? So the more loans you paid off, the higher your score should be. You can do this by sending copies of the quantum state. You don't give them enough data to actually learn what your underlying function f is, but you do give them enough copies of the data in order to be able to test certain properties of f. So you're able to do this without revealing what the underlying algorithm is. And one more thing before I get into our results. Now that we've written our resources or our access models like this, we get this very nice hierarchy of resources. Quantum queries can reproduce everything that classical queries can do, and classical queries can reproduce everything that classical samples can do. And analogously, quantum queries can reproduce quantum samples, and quantum samples can reproduce what classical samples can do. So we get this very nice hierarchy of resources. Okay, now what are our results? So our work is essentially an exploration of this model, asking various questions in property testing and understanding various things about quantum data and quantum examples. So first, we provide quantum testers for monotonicity, symmetry, and triangle freeness. We find that they outperform classical passive testers and are comparable with classical query-based testers. I'll talk a bit later about the actual algorithms if there's time. But here you can see that for monotonicity, we have an O of square root n copy complexity algorithm, and for symmetry and triangle freeness, we achieve constant sample complexity, whereas with classical samples, you require n to the 1/4 or at least n dependence. Next, there are three properties in the literature. They are K-Junta testing, the Bernstein-Vazirani algorithm, and correlation. And these algorithms don't actually require quantum query access. Rather, all they do with the quantum query is create superpositions of the state, and then the underlying algorithm can be thought of as just using quantum examples. But all three of these algorithms, the way they work is that they use Fourier sampling. So they use Fourier sampling to say something about the function f. So a natural question you can ask is Fourier sampling the only thing that these states are good for? Like maybe the best that you can do and the only thing that you can do with these states is just Fourier sample and then learn something about your function f from these Fourier samples. We find a property that only requires a constant number of copies of the quantum state, but it requires an exponential number of copies of the quantum state if you're only using classical data and Fourier samples. So in fact, the power of quantum data goes beyond just Fourier sampling. Our next result is an exploration of lower bounds. So in property testing, lower bounds are known to be notoriously hard. For monotonicity, there are ensembles that we know yield provably optimal lower bounds. There are two papers on this. First, the original paper on monotonicity by Goldreich et al., and then a second paper by Hadley-Black. And both of these find ensembles of functions that give you provably tight lower bounds in the classical setting. But when you try to embed these ensembles into the quantum sample setting, we find that they yield provably trivial lower bounds. So you get no better than the lower bound, I guess that something trivial would give you. I will also talk about this if there's time, but probably there will be. And then finally, there were two resources that I could not directly compare, and they were classical queries and quantum samples. So correlation requires an exponential number of classical queries, but only a constant number of quantum samples. So you can ask the question whether quantum samples are always more powerful than classical queries. We find a property that has the opposite characterization. So in fact, it requires an exponential number of quantum samples, but only a constant number of classical queries to resolve. So depending on the task, quantum samples and classical queries can each be exponentially more powerful than the other. So these two resources are, in fact, maximally incomparable. Okay, cool. So I'm actually going to talk about the last bullet point here, and we call this k-fold intersection estimation. So to introduce this, let's consider the problem of estimating the intersection of sets. So the setup is as follows. You're given subsets of the Boolean hypercube, S1 through Sk, and you're given access to a superposition over all elements in the Boolean hypercube. Okay, so this is very natural. And you're promised that either the intersection is at least a constant fraction or the intersection is empty. And your goal is to decide which of these cases holds. So you basically want to decide between S1, S2, and S3, is the middle ring or the middle section, is it 0 or is it at least a constant fraction of the Boolean hypercube? Okay. What happened? Okay. So let's do the twofold case. So you're given superposition access to two sets, A and B. So you're given a full superposition, and your goal is to estimate the intersection fraction. You can do this very simply by doing a swap test between A and B, and this will tell you the size of the intersection. What about threefold intersection? So you're given superposition access to three sets, and you want to estimate the intersection between A, B, and C. So for 2, you can do the swap test. For 3, your goal is now to estimate the intersection. And it turns out that this is actually exponentially hard, even if you're given superposition access to all 3 sets. And so I've been talking about function states, and I'm not going to try to convince you that the model I just talked about and function states are equivalent, but I hope you'll trust me when I say there's a way to define a Boolean function that corresponds to this problem, and you're given access to the quantum function state that encodes all 3 subsets, and your goal is analogous. Given access to copies of psi f, you want to decide whether the intersection is a constant fraction or it's exactly 0. And how are we going to prove that this is difficult? One natural thing to do is to take 2 ensembles of functions, one that is distributed on functions that satisfy the property that you care about, and the second is an ensemble of functions that are epsilon far from satisfying the property you care about. You draw f uniformly at random from either of the 2 distributions, and you're given access to t tensor copies, where t characterizes your sample complexity. And the distinguishability between the 2 ensembles is characterized by the trace norm. And so now the goal is to come up with 2 different distributions that will help you characterize the sample complexity, and then also prove that they're either easy or hard to distinguish. Okay, so these are the ensembles we're going to use. We're going to take uniformly random A, B, and C. So our first distribution is going to be uniformly random A, B, and C. And our second distribution is just going to be uniformly random A and B, and then C is going to be exactly equal to the symmetric difference between A and B. So in this case, everything in the D-node distribution has 0 intersection, and with high probability, everything in the first distribution has at least a constant overlap. And if we find the bound, we find that it's equal to t times 2 to the minus n over 2. And so if you want to be able to distinguish these with constant probability, you require at least an exponential number of copies. so 2 to the n over 2. And we get this very nice separation theorem. So quantumly, you require at least an exponential number of samples, but classically, only a constant number of queries suffice. And now I just want to give you some intuition for how we prove this. So what we're going to do is we're going to take both of these ensembles and project them onto the following subspace. So if you have t tensor copies of psi of f, every single coordinate, so the row coordinate and the column coordinate, can be thought of as a collection of t n-bit strings, as well as an association of which set they came from. That's our AI there, as well as the function output at that point. And we're going to project onto the subspace where all the function inputs x1 through xt are completely distinct. Okay, so this is just going to help make everything easier. And we can show that these original distributions are very close to the distributions where you've projected onto where everything is distinct. And then we claim that actually these projected ensembles are in fact equal to each other. And why is this? Well, so the projector forces all sampled inputs to be different. And now if you look at a single coordinate in your matrix, each row and each column contributes at most 2 membership checks. And in both models, random A, B, and C, and random A, B, and then C being the symmetric difference, these checks are identically distributed. So you essentially get no information from looking at a single element of this matrix which of these distributions it came from, whether it came from E0 or E1. And in fact, you can prove that because these two ensembles are equal and EI was very close to the projected ensembles, then E0 is approximately equal to E1, and we get this very nice separation theorem. Okay, so earlier we had a hierarchy of resources, and as I mentioned earlier, correlation tells us that classical queries, for correlation, you require an exponential number of classical queries, but a constant number of quantum samples. With this property, we see the opposite characterization, where you require an exponential number of quantum samples, but only a constant number of classical queries. So in fact, these two resources cannot be compared. And I think because I'm limited on time, I'm just going to talk about future work. So these are some of the things that we'd like to do with this data model, in addition to some of the things I've mentioned already. So one is to understand the difference in power between single copy testers and multi-copy testers. So I think there was a paper out on single copy stabilizer testing, but we want to understand, are there any properties related to classical data that maybe we can separate if we're allowed to act on multiple copies of the state versus just a single copy of the state. Another problem that we're really interested in is low degree testing. So can you determine the degree of your function f? And for this, we currently don't have any algorithms that go beyond d equal 2. So it'd be very interesting to get lower and upper bounds for this problem. Also, just generally improving our upper and lower bounds and finding new properties to test. Also, there's this very beautiful result I mentioned by Bly and Yuji Yoshida on characterizing passive classical testers with a constant sample complexity. We'd like to do the analogous thing for passive quantum testers and see if we can characterize the full set of passive quantum testers with constant sample complexity. And finally, the superposition that I've mentioned is one example of a quantum data set that you can use for classical properties, but it might not be the best quantum data set. So maybe you want to take random subsets of the Boolean hypercube and use those as data sets for testing classical properties. So we also are interested in knowing whether there are other quantum data sets that might be better suited for testing classical properties. If you want to look at references in the paper. So yeah, I think because I'm running out of time, I won't talk about any of our other results. But if you're interested in knowing upper bounds for any of our testers, if you're interested in talking about lower bounds or also about Fourier sampling, please feel free to come find me. But that's it. Thank you.
The session is open for questions.
Thank you. Thanks for the talk. I had two questions. One of them is actually more like to clarify something. So the separation you got,
Yeah.
it's between, I mean, it's not just between quantum data sampling and classical queries, but even like non-adaptive classical queries. Is
Yeah.
that right?
Yeah.
Okay, so, okay. Okay, the second question I had was more, have you looked at active testing? Do you have any idea if that changes the landscape or?
We're not sure yet. I think it does for some of our upper bounds, but I think yeah, we'd be curious if there's like differences between active and not active testing as well. Yeah.
Thanks.
Hi, thank you for the talk. I have somewhat of a general question.
Yeah.
So, as you showed that you need exponentially many copies for
Yeah.
three state overlaps. My question is, the two state overlaps are fairly common in like a lot of algorithms or just quantum
Yeah.
information processors, right? What kind of situations will be relevant for three state correlations, and what
Okay.
implication would this result have for that?
Yeah, so I'm very happy you asked this question. So we originally started this project as like a way to understand low degree testing, and then they turned out to be like a very large class of problems that you could solve, like a very, very large class. So basically all linear, like affine invariant properties could be testable if only we could do uh, three-state testing. So if you could do this problem, there's oh, it's not showing. Okay, if you could do this problem for like 3 or anything higher, it turns out there's like a very, very large class of problems that we could test. So we were really hoping that we could find a way to figure out the intersection of 3 sets from just copies of these states, but we ended up getting a negative result, and this is why this paper exists for, or part of the reason it exists.
Thanks. Well, I had a third question then. So this lower bound that you get, can I also see it as like a lower bound for a different problem, like distribution testing, where like you want to test quantumly if your distribution is uniform on some subset of the domain, and then you give an exponential lower bound for that?
So I can't really hear the question.
Oh, so this can also use that to see that like you prove a lower bound for a different problem, which is like generalized uniformity testing, where like I give you a probability distribution over the hypercube, and I promise you that either it is uniform on some subset or it's far from that.
Oh, are you asking if you can use this for that
Yeah,
question?
or like if that implies that directly.
Oh, that's a good question. I haven't thought about this, and I'm a bit jet lagged, so I'll probably give you the wrong answer. But yeah, but that's a good question. Yeah, so maybe I think this might be able to give you a direct.
I have a question.
Yeah,
So this is a more of a general question. It's like you have used like this uniform superposition of like states generally, and
yeah.
so is it like the norm to study these like uniform superposition, or like can you like assign different weight like states with different weights and like some like distribution of weights where like it's easier to prove some properties or something like that?
Yeah, so I guess this is why I spent so much time talking about the motivation, because it's not really it's not really a model that's been like well studied in the literature. But we wanted to like motivate it, and then we had like a bunch of different questions that we asked. But you're absolutely right. Like if you're given like different weight, like you can assign different weights to different x's, for example, and then perhaps you can test an even broader class of properties. So I think I listed this as like one of the open questions. So be very curious if there's like other weights that are more.
Thank you. Just like an open question as well. Did you think about extending these results to learning tasks?
Sorry.
did you think about extending these results to learning tasks?
Oh yeah. So the beyond Fourier method, so like a property that only requires a constant number of quantum states versus exponential number of quantum states, we have a remark in our paper that we can extend the result to quantum learning as well. So we find a property where you can't just learn if you have only copies of the Fourier sample, but if you go beyond Fourier sampling, then you can actually learn. Yeah, so I think the other stuff, we haven't yet tried extending to learning.
Thank you.